In the first lab, we talk about understanding motion with constant velocity. Some concepts that are important in this lab include Newton's first law, second law, and the momentum principle, which we derive from Newton's second law. The second law states that the acceleration of an object is dependent upon two different variables, those being the net force acting upon the object and the mass of the object itself. Using Tracker, we analyze a video frame by frame so we can plot an object's position versus its time. And using GlowScript v Python, we create a more precise computational model using observations and formulas in the code. So to start, in my tracker model, I track my soccer ball moving from the left side of my screen to the right side of my screen. The axes that I chose make it so that the soccer ball is moving from the negative x-axis to the positive x-axis. I will play the video now. So this is what it looks like. So after plotting in Tracker, position versus time, this is what my graph looks like. A positive slope with the ball going from the negative to positive x-axis. The time versus x position has been tracked here in this chart as well. The data that we can take from Tracker and implement into the computational model to create a more precise model include the initial position and the time, the ball's initial velocity, which we can calculate with some initial data points in Tracker. We take the first couple of points, calculate delta r over delta t, and which yields a result of 1.24 meters per second. That's just taking these first two data points. And the last observation time being 0.733 seconds. So the total time, delta t, basically. Putting all that into GlowScript code yields this. In GlowScript, as you can see, the graph also has a positive slope, and the position versus time has been outputted below by the code. As opposed to generating a CSV file, this just outputs the position and time in the form of text output below. Copying that into a spreadsheet allows me to combine the time and experiment position for the tracker model with the time and the position generated by the more precise computational model below. Combining the two gives me this graph right here. And on this graph, we can see that the experiment position, the data points from Tracker, have a slightly less linear, have a slightly lesser slope than the slope for the the slope for the computational model. But they both have a positive slope and they both have a linear pattern, and they're relatively close to each other, which is ideally what we want. Now going back here, you can say that the inconsistencies that you see between these two data sets can be attributed to things like the ball appearing closer together between video frames than in reality. It might move front to back, which is not as perceivable when you're recording from the side. And things like friction, other external forces also affect the ball's rolling. So in the short amount of time, we assume that it has a constant velocity with zero acceleration. Other things, and finally, two other things to note, is that in Tracker, I oriented my axes so that the ball is being tracked from left to right, from the negative to positive x-axis. If I were to flip the axis from the ball moving from the negative to positive x-axis to the positive to negative, this would result in the graph and data being generated to have a negative slope. The graph would be mirrored across the x-axis. So let me show you what I mean. This graph right here would be basically mirrored across the x-axis, so the slope would be negative and the line would be going the direction I'm moving my cursor, essentially. Finally, in the computational model, we say that there's a zero net force on the ball rolling. This is because after the initial push on the ball to start rolling, we assume that the ball has a constant velocity in the short time that it was recorded. This will also mean that we have zero acceleration for the ball, right? So other forces that would cause the net zero acceleration in the ball include things that we didn't account for before, but these are all inherent forces that affect the rolling of the ball that we must account for if we're trying to have a more complete description of all the forces acting on the ball. Other forces acting on the ball would be things like gravity, the normal force corresponding to gravity, friction, and air resistance.